Hey everyone, in this video we're going to go through a residual analysis. So we did go through this in class, but I wanted to just go through the 3 questions at the very end, which were all past exam questions. So we'll do that together, just so you know where everything is. So we've got a residual analysis here. So we're kind of focusing on the residual plots in these notes, but everything else you need is also in this one here. So the least squares line and the coefficient of determination, especially if we just go down. Where are we? All right, so didn't want that one. All right, so interpreting your least squares line of best fit equation. So I've had a few people already ask me, how do I interpret it? We did do this in class. You just need to know these 2 sentences. So I would strongly encourage you to stick these into your bound book with the heading, how to interpret, all right? And then it's there. So you don't have to remember these sentences off by heart. If you have a great understanding of them, obviously you can go ahead and write them. You don't have to write it word for word, but the fact that you can just use this sentence for your interpretation, or these sentences for your interpretation, makes it easy. All right, have it in your bound book. All right, and then to interpret your coefficient of determination, remember we have this sentence here. All right, so just making sure that you have those 3 things at the ready when you're doing a residual analysis, because you'll be asked to interpret them. In addition to R, which is your correlation coefficient, also calculating your least squares regression line, but some students have been asking, what does it mean by interpret? Okay, so just those 3 sentences. Okay, so we're going to look at, so I'm going to skip on through most of these notes just to the questions at the end. So we've got 3, so I'll just showing them all. So 3 questions, one from the 2017 exam. These are all past exam questions. One from the 2016 exam and one from the 2019 exam. So what we've got here is a typical residual analysis question where you're kind of bringing everything together. There is one step beyond this, and that's when it's not linear. We have to go on and transform the data, but in this video we're not going to focus on transformations, so we're just going to focus on scatter plots that are linear, not scatter plots that are non-linear. All right, so let's make a start. I don't think it's going to be a long video, but it could be my famous last word. So let's aim for about 20 mins. I don't think it's going to go for that long. All right, the scatter plot shows the atmospheric pressure in hectopascals at 3 p.m. which is the variable pressure 3 p.m. plotted against the atmospheric pressure in hectopascals at 9 a.m. So the variable is pressure at 9 a.m. for 23 days in November. A least squared line has been fitted to the scatter plot, and then we have the least squares regression line. All right, you might, and I just called it the regression line. We do see it referred to as just the least squares line, but if I call it a regression line, it's the same thing. It's just the old language. Your calculator also refers to it as a regression line, so it's probably good that you're familiar that they're the same thing. All right, so we've got our 2 variables plotted. You're always going to have your explanatory variable on your x-axis. So remember, x explanatory, and then your response variable. We also know that 9 a.m. happens before 3 p.m., so kind of makes sense for it to be your explanatory. All right, so part A, interpret the slope of this least squares line in terms of the atmospheric pressure at this weather station at 9 a.m. and 3 p.m. So you have to go to your equation. You don't have to calculate the slope. It's been given to you. So 0.8894. So I'm going to have to really squeeze that in, but remember, I'm just going to use, if I just scroll back up a little bit, the 2 sentences we had, no, gone too far, 2 sentences we had in our notes. All right, so just here. All right, so we're interpreting the slope for this one. All right, the slope is whatever. This means the y variable, all right, our response variable on average increases or decreases. So you have to see whether it's a negative or a positive slope by B units for every 1 unit increase in the X variable. All right, so I don't have to keep flicking back and forth. I'm going to do my best to remember that sentence. So the slope is 0.8894. This means that on average, the Y variable, so pressure at 3 p.m. increases, because it's positive, by 0.8894, whatever the units are, so HPA, for every 1 HPA, all right, so 1 unit of increase at pressure 9 a.m. Now, the good thing is with your exams and your SACs, when they're assessed, sometimes you get sentences and then you're like, oh, that doesn't overly make sense. You just want to, we're just looking for the key parts. So we want to see that you've got your response variable there. We want to make sure you've got whether it's increasing or decreasing correct. And we want to see the slope. And we'd also want to see the 1. All right. So we can't say for every hectopascal, we need to have that 1 there, or some word that means that. So every single hectopascal, I don't know, it's just easier to write 1, guys. And then it's always increase at, of your explanatory variable. All right, use the equation of the least squares line to predict the atmospheric pressure at 3 p.m. So we usually make predictions for our Y when the atmospheric pressure at 9 a.m. is 1,225. So we're just doing that on the calculator. Whoops, go to main. All right, so we've got oops, I've got another one in there, 1.4 plus 0.8894, and we're just substituting in that 1,025. All right, and I've got my calculator on exact mode, so I can just change that. So 10, so we've got to do it as the nearest whole number. So just write it to more decimal places and then do your rounding. So 0.035, which is approximately 1023. You don't have to give units, easy peasy, just write your answer. You can kind of also see on our graph, if I go up from 1025 and I go across, we can see we get that. All right, so you could also read it for this one off your graph. Can't always read it off the graph, but we can also substitute it in. That one was done really well, 84%. Is the prediction made in part B an example of extrapolation or interpolation? So extrapolation means outside the data set, interpolation means inside the data set. So we're definitely inside. All right, what that means is at 1025, do I have points above that? Yes. Do I have points below that? Clearly yes. So it's within the data set. Okay, determine the residual when the atmospheric pressure at 9 a.m. is 1,013 hectopascals. Round your answer to the nearest whole number. This was 40%. That is really strange for a residual. So your residual equals your actual Y. So we can put the Y in. So your actual Y minus your predicted Y might help. So 1,013, so I can find that here. All right, so, can't read it off my graph, but I can see this actual value is 1,015. So I have to read that actual value. Sometimes you're given it in a table. So my actual is 1,015, so I can put that in. But my predicted I have to calculate with my equation. So let's go and do that. So same equation, I'm just going to copy it down, but we're substituting in a different value this time. So we want that 1013. All right, so 1012, we're doing it to the nearest whole number. So I'm going to have, well, it's going to be 3. Don't really need a calculator for that, but if not, let's just do it. Minus, I can drag that down all decimal places just to make sure it does round, so it rounds to 3. The mean and the standard deviation of pressure at 9 a.m. and pressure, so that was 40%. Like I think what sorry, let's go back to D. What students may have had trouble with was actually understanding how to read the actual value off the graph. All right, or maybe making an estimation. So we can actually see, here's the 1013. Here's your predicted. So we can actually see it's 1, 2, it is pretty close to 3. So, you know, this question here, when was this? 2019. I'm really surprised only 40% got that right. All right, let's move on to E. The mean and standard deviation of pressure at 9 a.m. and pressure at 3 p.m. for these 23 days are shown in the table. Use the information of the least squares line and the information in the table to show that the correlation coefficient for this data, so we want the R value, is at 0.966. So it's a show that question. All right, you can go ahead and if you had to calculate R, you could put all those points into your calculator. That would take you a very long time. So just remembering your formula. So if I go back to the other Word doc, let me just do that quickly. All right, remember you have this formula here, and we can see the formula for B has R in it. So for your slope has the R. So we just have to substitute in the standard deviation of Y and the standard deviation of X. All right, so let's just do that over here. So B equals R times SY over SX. So B is our slope given to us in the question up here, so 0.8894. R is what we're calculating. If it's a show that question, you can't substitute in the answer. Remember, it doesn't exist. All right, and then SY and SX. So the S just means our standard deviation of Y and our standard deviation of X. So we're only looking at this part here. So we've got to decide which one's our explanatory. All right, so there we go. All right, so we're going to have R times SY, which is 4.1884, over SX, which is 4.5477. You need to have all those values substituted. All right, it is a show that question, so you need to show basically all that substitution. I would even put that formula in so you can see where it's come from. All right, and then if you put solve on your calculator, you should get 0.966. What percentage of the variation in pressure at 3 p.m. is explained by the variation in pressure at 9 a.m.? Now, this question doesn't actually ask you in an explicit way what it wants. It is using the interpretation of R squared. So once you've done enough questions, you'll get used to the language like this. So we've got the variation. All right, that's what has given it away to me, that it's asking for the R squared. But where did we do that was on the other one, wasn't it? Let's go to the other doc. So just go down to the interpretation. No, next one. All right, so you can see here, this sentence it's used. So R squared times 100%, so that's your coefficient of determination. We always express it as a percentage of the variation in the response variable can be explained by the variation in the explanatory variable. So getting familiar with that interpretation will allow you to see that it's asking for R squared. Now, we were given R in the previous question. So all we need to do is square it. So 0.966 squared. And we're doing it as a percentage. So we multiply it by 100 and we're writing it to 1 decimal place, so 93.3%. Again, I would do more decimal places, but just because I said I wanted to go for 20 minutes and it's already 15 minutes, so let's move on. The residual plot associated with the least squared regression line is shown. All right, so here it is. The residual plot can be used to test one of the assumptions about the nature of the association between atmospheric pressure and the atmospheric pressure. What is this assumption? Basically that it's linear. So a residual plot tests whether it's linear or not linear. So the assumption of linearity, so the assumption that the association is linear. Between the variables is linear. All right. Then part 2, the residual plot does not support this assumption. Why not? It's because we've got a pattern there. All right. You basically, if it's linear, you want your dots randomly scattered. So if we go back to our original scatter plot, to me it looks pretty linear. I think because we've got these points, if I just get rid of this, it's slightly curved, but yeah. And we probably have more points below than above. So when we're doing our interpretation, so I hope you don't get motion sickness as I go through, yeah? All right, so type 1, randomly scattered, that's what we want for linear. All right, so remember this is our linear. And then if it shows a pattern, which is similar to type 2, now clearly it wouldn't be exactly like this because you would have more dots, or like the one we've got now is kind of more like that. All right, it's non-linear. So let's just go back and say why is it does not support it? Because there's a clear pattern, basically. Clear pattern. Or you could say the data point or the dots aren't randomly scattered, or the residual. I should say the residual values aren't randomly scattered. All right, so just using the interpretation that I've given you before, that I just showed you when I gave you motion sickness, back up here. All right, you can just refer to what they've written here. Sorry, I didn't know how far to go. All right, so this here, if it's the assumption that it's linear, right, it's randomly scattered. If not, you can say, I would just say the opposite of what we've got here, as opposed to saying this. All right, you could say a pattern, a clear pattern, and not randomly scattered. Okay, so you just got to be able to interpret that. All right, let's move on to the next question. Sorry guys, it's definitely going to be more than 20 minutes. All right, this was from the 2016 exam. The data in the table shows a sample of actual temperatures and apparent temperatures recorded at a weather station. A scatter plot of the data is shown. All right, and the data will be used to investigate the association between the two variables. It's always great to be given a scatter plot because we know that your actual temperature is your X because it's on your explanatory, it's X because it's on your X axis, and apparent is on your Y axis. All right, so in your table, it's just around the other way. All right, they're a bit sneaky like that. Use the scatter plot to describe the association between apparent temperature, excuse me, in terms of strength, direction, and form. All right, so when we're doing that, remember your strength is, you can get that from your R value, but I can see this is pretty strong. The direction is definitely positive, and I can see it's linear. So it's pretty self-explanatory, but you might need to go back to work out like the different words. So for strong, it's either weak, moderate, or strong. Direction's either positive or negative, and form is either linear or non-linear. All right, that should be in your notes. All right, determine the equation of the least squares line that can be used to predict the apparent temperature from the actual temperature. Copy and complete the following by adding the values of the intercept and the slope of this least squares line in the appropriate boxes, and we've got to do it to two significant figures. All right, so when we put it into our calculator, it's always a good idea to put your explanatory into list 1 and then your response into list 2. All right, so I'm going to just pause and do that. All right, so I put these values into my handheld calculator, but I might just quickly show you where you would do it. So menu, statistics, and then you need to put your values into list 1 and list 2. So just putting your explanatory into list 1 and your response, just being consistent just means later on you won't get confused. And then we go calculate regression linear reg, and so your X is list 1, Y is list 2. You can see in a previous question I did copy residuals. We won't bother with that here. Just make sure you've got Y equals A plus BX. If not, just choose it from the menu. Now this is for different data, so don't worry about my numbers there. So I've just done it on my handheld calculator. Now, when you're doing any rounding, especially with significant figures, because usually you just write it straight into the boxes, it's probably a good idea to write it above the box and then put your rounded in the box. So the value of A, I got negative 1.6511. I'm just going to do it to 4 decimal places. And then B, I got 0.94266. All right, doesn't matter. We're doing it to two significant figures. So the first one is going to be negative 1.7. All right, so that's your significant figures. Remember, if you needed to, you can use S round on your calculator. And then for the second one, it's going to be 0.94. All right, so just making sure you get your significant figures correct. You probably will see significant figures here more than anywhere else, all right, with your regression. So make sure you can do it here. When I said S round, so it's, let's just go into the main screen. So if you feel you're going to use this, you can find it and leave it on your calculator. You don't have to clear your calculator before you start. All right, so we just see how it's going to take a while to find it. So having it on your, gone too far, on your main screen before you start your SAC. Oh, went too far, sorry guys. So many S things. All right, so there we go. All right, and then you can put it in. So for the first one, we've got negative 1.6511, and we want it to two significant figures, so comma 2, and there we go, negative 1.7. Just for those of you who might be a little bit anxious about significant figures. All right, part 2. Interpret the intercept of the least squares line in terms of the variables apparent temperature and actual temperature. All right, 28%. That is crazy. All right, so we're interpreting the intercept. So before we did the slope, so this time we're doing the intercept. So let me just go up to here. All right, so the y-intercept is A. This means the y variable is A units when the x variable is 0 units. All right, I'm not going to do that first part because we got it there. So now I can't remember. This is why it's so good. You can have a bound book. The y variable is, okay. All right, so we don't write y variable. The apparent temperature is negative 1.7. What are the units? Degrees Celsius. When the actual temperature is 0 degrees Celsius. All right, so just going back. All right, so this means that apparent temperature is negative 1.7 when the actual temperature is 0 degrees Celsius. All right, easy, 28%. I'm thinking students may have got the things around the wrong way because that is very, very low. All right, the coefficient of determination for the residual. So coefficient of determination is R squared. Between the various apparent 0.97, interpret the coefficient in terms of these variables. So coefficient of determination is also in that other document. Let's find it. So we're going to scroll. Yep. All right, so we're going to convert it to a percentage of the variation in your response variable can be explained by the variation in the explanatory variable. So we've got 97% of the variation in apparent temperature, your Y variable, can be explained by the variation in actual temperature. See, like just having those sentences there. This 28% and 49% business should be much higher. Let me just make sure I've been consistent. Now, if you had to do it the other way, like if it said that's not explained, it's 3%. 3% has been explained by other variables. You do not have to list what they could be, because they could be anything. So 97% of the variation in apparent temperature, so I should write temperature there, can be explained by the variation in actual temperature. The other 3% can be explained by other variables. All right, part D, the residual plot obtained, blah, blah, blah. A residual plot can be used to test an assumption about the nature of the association between the two numerical variables. What is this assumption? That they are linear. They have a linear association, very similar to the previous one. Have a linear association. Does a residual plot support this assumption? Explain why. It's a bit it does look randomly scattered to me, so I would say yes. Residuals are randomly scattered. Above and below the x-axis. All right, moving along. All right, so this one's taken from the 2017 exam. The number of male moths caught in a trap set in a forest and the egg density in the forest are shown in the table below. All right, determine the equation of the least squares line that can be used to predict the egg density. So when we're making a prediction, that's going to be our Y, whatever we make a prediction from. So we're going to make, what we're predicting. So we're predicting the egg density. So egg density is our response variable, or our Y, which goes into list 2, and number of male moths is our explanatory. You can also see here, all right, it's given us, isn't that nice? Egg density tells us it's our Y. So when you're putting these values into your lists, all right, it just helps you do that. All right, so we have to round this to 1 decimal place, so not significant figures this time. I'm just wondering whether I need to. All right, so you can do that. I'm just conscious of time. Let's move on to part B, which I think is maybe separate. All right. The number of female moths caught in a trap in a forest and the egg density, so previously it was male moths, can also be examined. The scatter plot is shown, and we're being given the least squares line. So we don't need to copy it. All right, you've been given a hard copy. And on an exam, obviously, you don't need to copy it. It's just told you because it was in a textbook, doesn't want you to draw in the book. And draw the graph. Now, this question here, we've got to sketch this equation. Now, the problem that students often make is they see this as the y-intercept and then just go, all right, where's 100 on here? It's probably around here. 191, maybe a bit higher. All right, there it is. You've got to take note of your axes. So see how our x-axis starts at 10. So that's our starting point. So we have, when we're sketching, all right, and this is very important to put into your, where's that random S come from? I don't know. when sketching least squares lines. All right, we need an end point. Or we need two endpoints. So let's do start point and end. Start point and an end point. Now, when people are marking your exams or your SACs, they're the 2 points they're going to look for. So our starting point is going to be at x equals 10, and we've got to work out the corresponding y value. And the end point, I go, all right, what's at the other end? It's 60. So we're going to let x equal 60, or our x variable equals 60. And I'm going to do this on the calculator to show you. All right, so don't need any of that. Let's go back. All right, so I'll get rid of that. Okay, so our equation is 191 plus 31.3. So we're going to do the start point times 10. Number of female moths, 10. So we've got 504. And not that one, thank you. And then for our other one, we're just going to do 60. And we have 2,069. And it would even be good to put that on your SAC or on your exam. All right, so when we're plotting it, we've got 10, 504, which is awesome because we can see that's going to be, let's do that in a different color so it's a bit easier to see. It's my pink. All right, so we just there. And we're going up by 100 each time, so it's okay to, just be on 500 or slightly above 500. Then our other endpoint at 60 is 2,069. Now, this one's a little bit harder. We're going up by 100 each time. So 2,100, 2,200, 300, 400, and then we're at 2,500. So your dot has to be between those two lines. Now, when you're sketching, your graph has to go through those 2 points. Don't be sloppy with your lines, and you need to use a ruler. So it's going to be a bit hard for me to do here without a ruler. Let's just see how I go. It usually straightens up for me. I'm going to straighten up. Excuse me. Usually it straightens up. Let's try it again. If not, you're just going to have to... Oh, that's pretty straight. Oh, usually if I leave my finger on it, it straightens it for me. Not this time. All right, but, I can clearly see the two end points. All right, so you don't pick, say, 10 and 15 too close together. So when people are marking it, they're going to look for this starting point and this end point. If you deviate too much from that, it's going to be wrong. All right, so 26% of students got this question right. And I would say the issue they made is with that starting point. They would have had it as 191 when your x-axis doesn't start at 0, it starts at 10. So we need to put that as our start point, and then our end point is 60. All right, interpret the slope of the least squares line in terms of those variables. So we've done a few of these now. Look at how poorly it's done, considering that you can actually use your bound book, all right, and you just restate the sentence. Oh, where are you? Okay, so let's go back up to the slope, just because I'm a bit tired and I want to make sure I'm consistent. All right, so the slope. This means the y variable on average increases, decreases, blah, blah, blah. All right, so the slope is, let's start here. The slope is 31.3. This means that on average, even if you didn't have the phrase on average, you wouldn't probably be penalized. This means that on average, the egg density increases, density increases by 31.3 eggs per square meter. See how the units are in the brackets and up here? Square meter for every 1 increase in female moths. And then that's not a continuous variable, so it doesn't have units there. So in female moths. You need to have that 1 there. I wonder if that's why it was so poorly done. All right, you need to have that 1. All right, the egg density is 1500 when the number of female moths caught is 55. So it's telling you a point on the graph. Determine the residual value of the least squares line. Determine the residual value if the least squares line is used to predict the egg density. All right, so your residual, remember, is your actual y minus your predicted y. So our actual y at 1500 is 55. All right, so sorry, other way around. When female moths caught is 55, that's why it's probably good to have actual y as 1500, because I was like, no, that's our y variable. All right, and then we've got to use the 55 in our equation. So number of female moths. So I'm just going to do that on my calculator quickly. So 191 plus 31.3 times 55. All right, so we get 1912.5. How did I do that right? Because I'm not liking that decimal point. Okay. And it hasn't asked us to round, so I'm just going to have to leave it at that. So I get a negative value, 2.5. Now, if we just have a look, 55, all right, so you can actually see it's definitely below. So that's good. All right. You can use your scatter plot to check your answer. So negative 412.5. Your residuals, you do have to write all the decimal places unless it specifies otherwise. I'm just reading what the exam hacks say. Oh yeah, so pretty much what I just said. Make sure you get the sign in the residual questions. If rounding isn't asked for, give the full answer. All right, so even if it was, say, 1.1245, all right, if that's what's on your calculator and it didn't ask you to round, you write every single digit. All right, you don't go ahead and round unless it asks you to round. All right, last question. Double the time I thought this video was going to take. The correlation coefficient is R equals blah, blah, blah. Determine the percentage of the variation. Okay, so again, it's asking for R squared. And we know that based on the this part here. Percentage of variation refers to your R squared value. It isn't asking you to interpret it. It's basically done the interpretation in the question. It just wants your R squared. So we can just square that value on our calc. So 0.862. And I can't believe this question wasn't done well. Actually, and it has to be as a percentage, so we'll multiply it by 100. The fact that it wasn't done well is because students wouldn't have picked up. It was asking for R squared, I would say. We're doing it to one decimal place, so 74.3%. All right, if it had to be not explained, then we do the opposite, which would be 25.7. So 25.7 would be other factors. And I'm not getting into the egg density and moths and so forth right now. All right, I hope that helps. You do need to know, every exam has something similar to this. Your SAC will have something similar to this. So make sure you get used to the interpretation. Very, very important. All right, bye. Bye, guys.